We're going to talk about the radiator fan. The radiator fan ensures that there's always a flow of air across the radiator even when the vehicle's not moving. So it basically adds an additional bit, a bonus amount of cooling to the radiator. And it only does that when the engine needs to be cooled. So there's a temperature sensor. When the coolant temperature is high, the ECU switches on the electric fan. Now, traditionally or historically, fans were driven by a belt from the crankshaft, typically along with the water pump and the alternator, or the fan was just bolted directly onto the crankshaft pulley or maybe onto the water pump pulley, but in any way, it was just attached directly to some part of the engine that's already spinning. In the UK, we often still call the accessory belt or the drive belt a fan belt, even though it's been a very, very long time since that belt was actually used to drive a fan. Now, the closer a fan is to the radiator, the better. You can see how close we are here. Any more than a few inches, and the fan loses its ability to pull air through the radiator itself. Nowadays, most cars, like this one, use an electric fan, which is easily controlled, and you can position it separately from the engine. So here we're out of line with the engine if you look along. That allows a bit more flexibility, and with a lot of vehicles you have a transverse engine, so the engine would be rotated 90 degrees in this direction. You wouldn't be able to run a fan off the engine's rotating parts. And an electric fan provides cooling at a good speed when the vehicle is idling, and that's when we really want the most cooling. So the problem with a fan that's powered directly off the engine is that it's coupled directly to the engine speed, so the rotation of the fan directly related to the speed of the engine, and often we need the most cooling when the engine is idling. That's one of the other benefits of an electric fan. Now, the fan is only needed when the natural airflow from the vehicle's motion through the radiator is too low to provide the cooling that we need. So that might be sitting in traffic or driving up a hill, but a lot of the time the fan isn't needed at all. So we need some way to control the fan so that it's not running all the time, i.e. we're only running the fan when we need it and not wasting that energy that we can put to our wheels. So electric fans like this one are controlled electrically, but fans that are driven directly by the engine, we're talking about viscous drive or viscous clutch driven fans, and I don't have one here to play with, but basically a viscous fan is driven by the engine via a clutch that controls whether the fan spins or not. There's a load of different designs out there. It's some real fancy mechanical engineering. Those sort of fans are popular on big inline engines, particularly in older cars. You can't put one, as we said, on a transverse engine because the pulleys are in the wrong position. You'll find those type of fans even on modern engines in 4x4s and commercial trucks because they've really got the power to pull air in. And those vehicles tend to move slower and need more cooling. So by far the most common type of fan that you'll find in use today is an electric fan just like this one. And it's basically just an electric motor on the centre and some fan blades around the outside. Electric fans have a few advantages. They deliver a more consistent airspeed, particularly at low RPMs, and they are more controllable. Plus, no engine power is being used to drive the fan directly. That sort of engine power that's used to drive the fan is known as parasitic horsepower loss, where you've got engine power being used to drive an ancillary that you don't need. Also, electric fans can fit into a much tighter space in the engine bay, so you've got a little bit of packaging flexibility in terms of putting an engine into a car. Now there's two setups of fan, a pusher and a puller type of fan. Puller fans like this one are the most efficient and they're the standard fit. They mount onto the back of the radiator and they pull the air through. Now a pusher setup would be used where you've not got the space behind the radiator here. And when a fan pushes air, i.e. the fan is on this side, it pushes the air through the radiator, it's a lot less efficient. About 20% of the air just bounces off the radiator itself. So you might find a pusher fan incident that you can add a pusher fan on. So maybe there's not space behind for another fan, but if you're doing a lot of towing or something, maybe you'd add a pusher fan. Note that different models of the same car might have different powered fans. In fact, let's have a look at this fan. I've got another one here. Let's spin it up, see it in action, and actually see why I'm a little bit scared of these fans. I find them, they're actually one of the things on a car which, you know, you can appreciate that the fuel tank is probably quite dangerous. You can appreciate that probably you shouldn't put your hand into this belt. But these fans spin very, very fast. And I've seen a terrible picture of someone with a fan blade stuck in their neck somewhere. So on the whole, I'm a little bit fearful of these. We'll run one up, see how much power it takes, and actually see, you know, how much force is coming, because this is not just, you know, a delicate little desktop fan. It's a pretty powerful bit of kit. Got my safety specs because I'm petrified of this. So what we have here is a fan, exactly the same as what's on the car. This one suffered some damage in the journey here, who knows. What I want to do is I want to show that these fans move some serious volume of air. So this thing, at normal speed, is moving 20 cubic feet per second. And if you think that the diameter of this is probably, what, 14 inches, something like that, so a little over a foot. If you imagine a column 20 feet long coming off this fan, that's how much air is going through here every second. So we can adjust the speed here. So let's get this thing spinning and see where we're at. Now, I would say around there, around 6 volts, that would be a fairly fast desktop fan, or you know, one of these fans that you have at home. But we move this up, let's get up to 12 volts, and now you really see the power of it. It's actually pretty scary. And now we hit 12 volts, takes 6.2 amps, and that is shifting some serious air. We'll bring this back down. I don't know if you can hear my heart rate there. At least you can hear how noisy the fan is. I don't know why this thing scares me so much, but you certainly would not want your fingers in there when this was running full clip. I don't know if it'd take a finger clean off, but I suspect it would. In fact, it definitely would. Anyway, there's different types of fan on the same vehicle. Let me take my specs off. You might find that the same car has different ratings of fan depending on the cooling requirements. So, you know, a car with a 1.6 engine may have a smaller fan or lower wattage of fan than, for example, a 2.5 in the same vehicle. Or you have air conditioning, which would require a little bit more cooling. Sometimes, like on this vehicle, on the Miata, you have a second fan for air conditioning. So we've just seen that this thing takes 6-7 amps when it's running full clip. We talked about the viscous fan on engines where it's directly driven by the engine and the clutch disables the fan when it's not needed. Now, an electric fan also uses power, and although it's not taking it directly from the engine, if this fan is running, the alternator needs to generate another 7 amps of power. Now, that takes energy from the engine. Obviously, the engine uses more power to spin that energized alternator. If you've seen the episode, the wonderful episode, maybe the best episode ever on alternators, then you'll understand that that requirement for an additional 7 amps makes the alternator harder to turn and sucks away some of the juice from the engine that we want to propel us down the highway like kings. The fan should cover as much area of the radiator core as possible. The more of the core that it covers, the more tubes of coolant are being cooled by the airflow that it pulls through. So using a shroud, which is this plastic surround, lets us basically hammer a square chunk of air through a round hole. Because the fan spins in a circle, using a shroud, we can actually pull air through a greater surface area and put that through. So the shrouding around the radiator is very, very important, and it ensures that the air is being pulled through the radiator and not just swirled around kind of behind here. So a radiator fan without a shroud, without the rubber, sometimes you find rubber seals around the shroud, you've got to keep those in place, because without that, the fan a lot less effective. Fans are rated on their airflow using cubic feet per minute. So a typical 4-cylinder engine like this one is probably going to be rated for about 1,500 cubic feet per minute, and that goes up depending on the size of the engine. For example, a V8 might take 3,000 cubic feet per minute. So that's based on the cooling requirements of the engine. Another thing is a difference in fan blades. So fans can be noisy, and a fan with straight fan blades like this one is going to be noisier than S-shaped blades. Other considerations with blades, we've got the blade width, and we've got the pitch angle of the blade itself. And a quality fan will have the blades balanced. There'll be little metal clips that are fitted to the blades at the factory when they're balanced. And fans can be improved or made a little bit quieter by using concentric rings. So there might be a ring around the outside that ties the blades together, or even a ring around the outside and a second ring halfway along the blades. Those prevent the blades from wobbling, and they cut down on harmonic oscillation when the blades are spinning. It makes the fan less noisy, basically. The fan in this vehicle, or part of the vehicle that we've got here, is controlled by the car's ECU, by the computer system. Now, the ECU, ECM, in this case it's the PCM, that's what we call it with this particular vehicle, the powertrain control module, but essentially they're all just computers, ECUs. Anyway, the first episode where we talk about the ECU in this course will cover how the fan is turned on and off based on the coolant temperature sensor. But, spoiler alert, there's a coolant temperature sensor back here on the engine, and the ECU receives the temperature of the coolant from that sensor and then switches the fan on and off. So the ECU can't directly control the fan because the fan takes too much current. So electronic components, electronic switching circuits, they can only really handle currents in the hundreds of milliamps. And the fan, as we've seen, takes about 6 or 7 amps. So between the ECU and the fan is a relay, which sits about here. And what happens is the ECU sends a small current to the relay, turns the relay on, that sends a big current over to the fan. We've got a whole episode in the section on electrical systems all about relays and how they work. Now, the cooling fan will generally run any time that the air conditioning is on. So even if the coolant in the engine is cold and the fan is not required, if the air conditioning is on, then the fan will be running. So it sits kind of in parallel with the air conditioning fan. On this engine, if we had AC on this particular vehicle, there would be a second fan here for cooling that. One other thing is that these fans might stay on when the engine's turned off. So you sometimes hear the engine's turned off, you can still hear the fans spinning. That's just to ease the temperature of the coolant down and prevent heat soak, which is where the coolant and the engine actually rise in temperature as the cooling system stops functioning. So you might find that, and that is based on either a time delay or the coolant temperature in the engine. That is about it for fans. Next up, I think we are talking relays.